Let's just have a look at this, people. This is a view of Earth's magnetic field lines. So I've got this 3D model from the internet. Somebody has prepared it. My many thanks to them. And it was uploaded free of cost on the internet, and so I could use it. And it is viewing, it is being viewed in this SketchUp viewer or something. So let's see that there is this tiny Earth at the center, and there are so many magnetic field lines which are shown around. And this is a wonderful model. So let me just zoom into it and show you how it looks like in a close-up view. So you see, this is how it looks like. You see, there is Africa here. Then as I turn around, I get to India here, and as I turn around further, maybe China here somewhere. And then as I keep on turning around, this is Japan somewhere, those islands that make up Japan. Here you have got this North Pole, right? So this is the Arctic Circle, people, on the top. That white cap which you see, that's the topmost part of the Earth. And the bottommost part is here, people. This is Antarctica, and slightly away basically. So you see that the coldest part is this, and here you have that ice cap. Here you just have water, and that is because of the tilt that Earth has when it goes around the sun, right? And you see Australia here, and then you have the two Americas, right? So we have got this 3D model of the Earth, and it shows you the magnetic field lines. Now you see that the magnetic field lines are bunching together near the North Pole, that's the Arctic Circle, and also near Antarctica here. So they are bunching together at Antarctica also, right? You can see this view, and I have turned the Earth upside down. So in this view you see that the lines are again bunching together at this place. Now apart from that, apart from the bunching of those field lines at the North Pole and the South Pole, you will also see that at the same place on the Earth's surface they have shown multiple lines. For example, now I don't know how much will you be able to focus on this, but let's say this line, the one on which the mouse is hovering right now. So this line is one line, then this line is another line, and they are at the same place on the Earth's surface. Now you see I have brought into focus, so this is one, this is the other one, two. Now you have got this line 3, and maybe this another line 4. They are at the same place on the Earth's surface. You see these 4 lines. Now you will be able to clearly see them. 1, 2, 3 and 4. So these 4 lines are at the same place, and I can even rotate the Earth and I can align them together. Now see, those 4 lines are aligned together here, right? The only change that is there between them is that they are one is bigger than the other. So you have the smallest one inside, then there is the outer one, then there, of course there are not 4 of them, there are infinite of them, but then in this animation we have got 4 of them, and those 4 can be made to coincide with each other in this view like this. So they are almost now coinciding, and I'm seeing this Earth from this view, and you see that when they coincide, they lie exactly north-south. So if you say at the top is Earth's geographical north and at the bottom is Earth's geographical south, then this black single line which I see from this view is exactly north-south. But that may not be this, it may not be the case at some other place. So maybe I'll just take a screenshot of this and I'll keep this for future view. So just allow me. Let me then show you another view of this. So let's go to another view, people. Let us go somewhere close to India. So where is our India here? India is somewhere here. Cool. And as you will be able to see, near India there are again these 4-5 lines. You see that there is one line, that's the innermost line, this one. Then there is another line, second line. Then there is a third line. Then you have got a 4th line, and so on. And by turning the animated model suitably, what I can do is you see that I'm bringing together those lines, and now, yeah, you see this view. All those magnetic field lines are looking like one when I view it from here, right? So when I view the model from this side, all those magnetic field lines, they are one over the other. So the smaller ones will be much closer to the Earth's surface, the larger ones will be much farther off from the Earth's surface, but all of them are right below each other, and that's the reason I'm not able to see 2 or 3 of them. I'm just able to see this one single line. And if I tilt it, I will again be able to see those lines 1, 2, 3, 4, 5 and so on. But the interesting thing which you note is this. The interesting thing is that when you look at this Earth and you see where is geographical north and where is geographical south, you still know that geographical north is here and geographical south is here, but you see that the field line now is tilted. It's not exactly geographical north south. The earlier view, which we had, the earlier view that was close to South America somewhere, which we had, this magnetic field line was exactly geographical north, geographical south. But now, close to India, this field line is not exactly geographical north and geographical south. It makes a small angle with that. Right. So this is another thing that you should note, and maybe I will just take a screenshot of this. So now another thing which I want you to understand and appreciate is this. Suppose in this view, let us say I cut India into two pieces, and of course I'm not saying it geographically or politically. I'm just saying, just imagine that you're doing it. So I'm not an anti-national people. So let's say that we have a vertical plane with which we are cutting up India into two pieces like this, and I align that vertical plane exactly along this single line that I'm seeing. So you can think of a vertical plane that is on the Earth's surface and then protruding up from the Earth's surface, then protruding up from the Earth's surface, and then so this vertical plane which you have, which you can incline at a certain angle to the Earth's geographical north and geographical south axis, that vertical plane will contain all these 5 magnetic field lines, which you can now see distinctly in this view. So there is 1, 2, 3, 4, 5. So you will have this vertical plane which will have all those 5 lines, and I will show you the side view in a moment, but that's what is going to happen. And can I show you the side view? It will be a bit tough, but I think I can manage. Yeah, you can see from the side view, yes, here is India and here are those lines. So 1, 2, 3. So these lines, I think, yeah, these ones. This is one very close to the Earth's surface. This is another one. This is a third one probably. Here will be some fourth one. So those lines are all lying in one vertical plane. And this should give you some idea about the fact that the vertical plane in which all those lines lie, right? So now I'm aligning all these lines, which are above China, in one single vertical plane. And now, actually, if I cut China up into two pieces, which I'm going to do because I'm a nationalistic Indian people. So if I chop up China into two pieces here, with this vertical plane, and then I view it from that side, that cross section, then I will be able to see all the field lines, the smaller one, the larger one, the larger one, and the largest one in that vertical plane. So there is a vertical plane at any place that contains all the magnetic field lines, and that vertical plane may not be exactly geographical north-south. That vertical plane may make a small angle with the geographical north-south plane. Here we are. I think after seeing some of that, you will be ready to appreciate something which is called the angle of declination. So first, magnetic field of Earth, its elements. So when I say elements, I am speaking about the different terms that we use and the different things that they represent and how those things together define the magnetic field of Earth. So first of all, let me take Earth to be a sphere here. And to show you where that Earth is, I'm just going to draw a spherical ball. Of course, it will be looking like a circle, people. So let's say this is the Earth in our view. And this Earth has got a geographical north, has got a geographical south. So let me draw that line too. So maybe the line comes from here and it's like this. So you've got a geographical north and a geographical south. So you've got, this is probably geographical north, let me call it GN in short, and geographical south, and let me call it GS for short. And there is a bar magnet inside the Earth, And let me show you that bar magnet to begin with as a rectangle that is aligned exactly geographical north and geographical south. So maybe this is the bar magnet. Let us first clarify a few things. So when we started studying magnetism, it was sometime in 15th, 16th century or maybe even earlier. That was the time when we got hold of something called the bar magnet, or at that time it was known as the lodestone. And the lodestones were used to find out directions. And one of their properties was very interesting, and that property was that if you hang a lodestone with the help of a string or something from its center point, then it always comes to rest in a geographical north-south direction. Not exactly sometimes, but most likely in that direction. So you could use a freely suspended lodestone to get an idea of approximate north-south direction. That was the use of lodestones. And then when we started studying their properties, we found out that they have two different kinds of poles, and unlike poles attract and the like poles repel. Now how could we have found this out? Very simple. You take two lodestones. So let's say you have got one lodestone, this one, and you have suspended it freely from the center, and the end point that goes towards Earth's north, you mark that with an orange dot or something, or maybe a bit of charcoal. So let me take that charcoal kind of an effect. So you mark it with the help of a charcoal somewhere, like this. And then what you do is you take another lodestone. So you take another lodestone like this on the right hand side here. You suspend this lodestone also with the help of a string from its center, and you wait and see which end of this lodestone points towards Earth's north, and you mark that in charcoal. Fine. So you have marked this end in charcoal too. And now we have got the charcoal marked ends which were going towards Earth's north, and so they should be similar to each other. And the other sides, because they were going towards Earth's south, they should be similar to each other, which are the non-charcoal marked ends. And now the experiments are very easy to perform. You take the two lodestones, and what you do is you bring their charcoal ends together like this, and like this, and you will see that they will repel each other. You bring their non-charcoal ends together, like I'm going to show you here, perhaps. Like this perhaps. So you bring their non-charcoal ends together and they are again going to repel. So in the first view, these guys they repel. In the second view, these guys they repel. And then if you bring their unlike poles together, then they will start attracting each other. So this we learned by this very simple experiment, and with the knowledge that we had about charges, we understood that there are two different kinds of poles here. We started calling one of them north and the other one south. Okay, so cool. One of them is called north and the other one is called south. And the north was the label that was given to the one that was pointing towards Earth's north. So this guy, the charcoal marked one, will be called north then. And in the other one, the charcoal marked one will be called north. And now some, smart guy came in and he said, wait, if this is the guy that points towards Earth's north, that means somebody is attracting it towards Earth's north, then the guy who is attracting this towards Earth's north should actually be the south pole of some magnet. And so keep in mind that near the geographical north, we have got the south pole of the bar magnet that is present inside the Earth. And near the geographical south, we have got the north pole of the bar magnet that is present inside the Earth. So there's south pole of this magnet here and the north pole of this magnet here, and the south pole of this magnet attracts the north pole of this lodestone which we have. But nevertheless, if you draw a line that goes through Earth's bar magnet, which is the axial line of Earth's bar magnet, we are going to call it magnetic north-south line, and we are going to call this guy magnetic north. So please keep in mind that there is a change in the notations. So here we have south, here we have north, but still we will call it magnetic north. That's how the convention is. And we will still call this guy magnetic south. And like you saw in the model, now there will be a very large number of field lines which will be emitted by the north of this bar magnet. So there will be field lines that are going to go out like this, like this, like this, and like this. And these field lines will branch around and they will just go around the earth like this, and then they will be going into the south pole like this, like this, like this. And within the south pole, and within the magnet, they will be moving from south to north in straight lines, something like this. And then once they come back to the north, they will again branch out and they will be closed curves. Fine, so all this is very fine. But there are some interesting things that we have learned over time with our experience. And those things are these. First is that there is no requirement for this bar magnet to be perfectly aligned with the north-south direction. So let me erase a few things here, and I think I have erased some important things also. So let me erase all these things, people. And now what we have is so we have got a bar magnet here. Let me draw the bar magnet again. And this bar magnet may not be aligned like this all the time. It may make an angle sometimes. So in this figure, you have near the top, you have got geographic north as well as magnetic north. And here you have got geographic south as well as magnetic south. But this need not be so. So you have got the same earth, you have got the same geographic north and south, but then the magnet may be tilted in a different view. So what may happen is you may have the magnet not placed like this, but placed in some other manner that I'm going to show you. So what may happen is that you have a magnet placed like this with its south there and north here, and then the field lines will be branching out from here like this, and then they will be going back into the south pole like that. So you will have a structure of this kind. So how can we make sense of this structure, or do we know that this really exists, or what happens, and so on and so forth? So all these questions. Yes, it does happen. Let's think of this from a 3D viewpoint, and let's also have a three-dimensional coordinate system to help us. So let's take a three-dimensional coordinate system, people. Let's say this is the coordinate system that I want to show you. Yeah, and let us also say that there is a bar magnet that is shown by a rectangle, something like this, which is kept along the z-axis. And there are some viewers who want to view this. So maybe there is a person A standing here near the x-axis side. So this guy A, he sees the bar magnet and he says that it appears like a flat line. And you ask him what is the length of that line, and he says that the length of this line is capital L. Capital L is the total length of bar magnet. Fine, you agree with him. You say yes, fine. The length of the bar magnet is actually L. So whatever he is seeing must be correct. Let's keep another observer, an observer B, on the y-axis somewhere. So you have got an observer B who is looking at this bar magnet from the y-axis side, and you again ask him the same question. He says yes, it is aligned along the z-axis and its length is L. And there is another observer who is standing on the z-axis here somewhere, and he is viewing from that side. And when you ask him, he says it appears like a dot. It appears like a dot, it is a geometric dot, and that's all, it has got zero length. And you agree with him too. Yes, fine, very good. Now what I will do is I will change the orientation of this magnet slightly. So let me copy this figure, let me paste it here, and let me say that this magnet undergoes a rotation. So this magnet will no longer appear like this. The magnet has undergone a rotation, let us say, about the y-axis. So when the magnet undergoes a rotation about y-axis, it will be still in the xz plane. So the magnet may look like this, something like this, right, in the XZ plane. And this length, the actual length, so I have drawn a too big bar magnet, I believe, people, maybe like this. Yeah. And this length is still L. This is the actual length of the magnet. And now you ask these guys, what do they see? So when you look at this guy A and you ask him, what do you see? He says, I see a bar magnet that is inclined, he will say that I see a bar magnet that is aligned along the z-axis and whose length is Lx, this much. He says the length of this bar magnet is Lx. That's all. Then you go for this guy who is seeing everything from the y-axis side and you ask him, what is the bar magnet doing and where is it and how much is its length? And he will say that the length is still L, the complete length. But now it is no longer aligned along the z-axis. It is making an angle with the z-axis. And that angle in this figure is going to be, let us say, in fact I should show it in orange color because this is the orange observer that I'm talking about. So he will say that the angle will be some theta. And then you ask this guy, the one who was seeing everything from the z-axis side, and he says, oh wow, it's not a point anymore, now it's a rod with a certain length. And you ask him how long, and he says that the length of this rod is this much. This is the length of rod that he sees, and let me say this is Lz. And when you ask him what is the alignment, he says it is aligned along the x-axis, it is that much long, it's along the x-axis. So you see that the views of these three people have differed. Only one of them now is able to see the true length, and that's B. And A and this guy C will not be able to see the true length. So let me call this observer C, and let me call this observer also here C, people. So this guy is not able to see the true length, and he sees the bar magnet to be along the x-axis, he sees the bar magnet to be along the z-axis, and he also doesn't see the true length. Only B is able to see the true length. But now suppose the bar magnet again rotates, this time not about y-axis, this time maybe it undergoes a rotation about x-axis. So now it will be tilted in some manner. This bar magnet will have a tilt, maybe like this, so that its length that is now viewed by B will also be different, by A will also be different, and by C will also be different, and the angles that they will say it makes with their axis, with the z-axis, let us say, will also be different. And this is what you saw in that three-dimensional view which I was showing you. So let me bring in that view again. So these were the two views whose screenshots I had taken then, and let me just show you what is happening here. So somebody who is viewing that bar magnet from this side will say that the bar magnet really looks like this. The bar magnet is this bar magnet, and one of the field lines is going right like this. Right, of course, the field line that I have drawn here is not the field line that goes through the bar magnet. The field line that I am showing you in this view is the one that is in the air. So the north pole of the bar magnet is down somewhere here. This is north. The south pole of the bar magnet is here somewhere. This is south. And the field line first goes out of the north pole. So let me show that in orange. It goes out like this. Right. I don't know if it is clear. So it goes out like this. Then it turns back, and then it goes up, and while it is going up, like this, and then it goes back into the south pole like that, this up view is basically this black line here, which I'm going to draw in a pink color. So this one, it is this line here, people. So while going through like this, you have been able to see that line outside the earth, and then it goes away into the south pole there of that bar magnet. And this person who is viewing it from here will say that the magnet is aligned right along the geographical north-south axis. But somebody standing somewhere in India will differ. He will say, what? Those South Africans have gone crazy, This is the bar magnet, and it definitely makes an angle with the geographical north-south. The north pole of the bar magnet is here somewhere. The south pole is near the top somewhere. Let me show that in a different color, or maybe at a different place. So there is a south pole, and the field line goes like this. It goes out, then it turns back, and then it turns back, and then it turns back, and then it goes back into the south pole, but the region where it is turning back and going, that is actually this black line, right? So I have arranged the view such that all the lines were overlapping each other. So that is now this pink line, people, right? So this angle that the bar magnet appears to make with the geographical north-south axis is called angle of declination. So let me go for the first definition here. Let me first go for magnetic meridians definition. Magnetic meridian. Because this is a word that will appear often, you should know what a magnetic meridian is. So standing at a place, standing at a point on the Earth's surface, the vertical plane that contains all the magnetic field lines at that place or at that point is called the magnetic meridian. So magnetic meridian is a vertical plane. It's the name of a vertical plane, people. Keep that in mind. That is very much important. So magnetic meridian is the name of a vertical plane. Which vertical plane? It's a very special vertical plane. It's a vertical plane that contains all the magnetic field lines which are going above that point. So keep in mind this. The next one that you need is the angle of declination. Angle of declination. Now what is this guy, angle of declination? This is the angle made by, this is the angle made by the magnetic meridian with the geographical north-south plane. Keep in mind this also. So angle of declination is the angle that is made by the magnetic meridian. So this is one plane with the geographical north-south plane. So here in this figure, the magnetic meridian is lying along the geographical north-south. So for this case, the angle of declination should be 0 degrees. Angle of declination at this place is roughly 0 degrees. We can see it will be a small angle, it will be maybe 1 or 2 degrees, who knows, but then it's close enough to 0. So I can then claim that if you are standing maybe in Brazil somewhere or maybe Argentina somewhere, and you are trying to find out the angle of declination, it will very well turn out to be almost 0 degrees. But then if you are standing in India somewhere, then the angle will be around 8 to 10 degrees or something. So you have got a geographical north-south line, and you have got the bar magnet which is inclined to that geographical north-south line, and the angle that exists between the bar magnet and that north-south line is probably around 8 to 10 degrees, 15 degrees. Who knows, it's some angle. It will have to be found using some kind of basic charts. So I can simply say that angle of declination here will be angle of declination is typically around 10 degrees to 15 degrees, who knows, we'll have to find out the exact number. But the most interesting point is that this angle will differ from one place to the other. Of course, its variation will not be so much that I'm in my house and I find angle of declination as something, and then I go to maybe one of yours house and then I see that the angle of declination is something else. No, that won't happen because we live very close by geographically. So what happens is that the variations in Earth's magnetic field over such a small geographical region are imperceptible. But then if you were to change your location wildly, like say from India you go to maybe UK or somewhere, or not even that, from India probably you go to China or someplace, or so the angle of declination will keep on changing. So over reasonable amounts of distance, the angle of declination will definitely change. So we should know that the angle of declination is different at different places. It differs from place to place. And before finishing this angle of declination part, I will just mention that it is very important for navigators to know the angle of declination at a certain place. You cannot just rely on a compass, and now you have understood why you can't really rely on a compass. So the idea is very simple. Let me take you back to that animation for a moment. So to show you the importance of this angle of declination for navigators, I have chosen this image from that 3D model. So what you do is maybe you are standing at some place here in India. So you are standing at some place called A, and you want to go to a place B which is due north of A. So maybe there is, let's say you are standing in Chennai somewhere. Let me draw Chennai here. So you are standing in Chennai here somewhere, and you want to go to probably Lucknow. Lucknow will be somewhere here, somewhere there. So I'm not sure where exactly it is, but let's just say that I know where it is, and I'm pointing it out on the map to you. This blue dot here, not blue, let me make it black or something. So this black dot here is Lucknow, and you know the information that Lucknow is due north of Chennai. So you walk along that line, the north line, and then you will reach Chennai. So what you do is you arrange for a compass, and you hold the compass in your palm. So the compass needle is in a horizontal plane, and the compass needle deflects, and it shows you this direction because it is affected by the magnetic field. So what the compass needle shows you is this orange line, and then you are like, yeah, that is north. So you keep on walking, and then maybe you end up somewhere to the left of Lucknow, but you won't end up exactly at Lucknow. So that's why it is very important for you to know what is the specific angle of declination at that particular place. So maybe you had that information. If you knew that the declination in India somewhere is around 15 degrees and it is westwards, that means the magnet will show you maybe 15 degrees west direction to true north. So what you will do is, whenever the magnet shows you something, you will turn 15 degrees towards east, and then you will start walking, and then you will reach Lucknow. So that's the importance of this angle of declination for navigators. But for us people who are doing physics, maybe not very useful presently. For us, the angle that is important right now is called the angle of dip, and let me get to it in a moment. Now there is another angle that I want you to focus on, and that angle is here, people. Now let's say we are looking at India, and we are looking at the magnetic field lines that are right above India. So there are 4 or 5 lines. Now I'm bringing them one over the other, and job done. So they are almost overlapping in this view. Now I just want to have a look at a different view. So maybe I just have a look at this view, where you see this is the line that went over India. And at the top you see how it is going into the earth there. So this field line is curving, and it goes into the earth right there. And let's focus on this particular line. That is the line which is closest to my mouse here. So this particular line, yeah, this one, people. So let's have a look at this particular line, and let me take this view for future demonstration. And let me show you a different view. Now you know that now I'm seeing the northern hemisphere. So let me go and see what happens at the southern hemisphere. You see that at the southern hemisphere, at this place, the lines are coming out of the earth. And if I just turn the earth upside down, which I can do here but not in real life, people. So let me just turn the earth upside down and show you what's happening. You see that the lines follow almost the same pattern as what they were doing near the North Pole. So you see this particular line. This particular line goes into this place, Antarctica, and the place where it is going into the earth in the same manner as it was going into the earth here at this end, right? And seeing this field line in this view, you won't be able to say whether it emerges out of here or whether it goes into the earth here, because there are no natural arrows on magnetic field lines to show they are going from north to south. But then we know that there is north pole of earth's magnet here, so this line must be emerging out here. So let me take this particular view, people, of that line which was right above Antarctica, and that line is this one. This is that line, people. This is this line that I'm talking about. So this line goes into Antarctica here, right? So it's not really going into Antarctica, it is actually coming out of Antarctica like this, and then it goes towards the northern hemisphere, where it turns like this into the earth. So let's take this view, maybe a better one. Yeah, maybe this one is better. Yeah, so I'll take this view. This is the line that I'm speaking about. So in Antarctica you can see two lines going in. I'm talking about the line that is closer to us, that is this line. I can as well speak about the other one also. They are following the same pattern. So let's have a look at these lines. And now I'm going to show you something in the other notebook. This was the view where I showed you one line that was right above India, and I guess that line, if I am not wrong, the one that I wanted to, that I wanted you to focus upon is this particular line, the pink one. Right, so this is the line that I want you to focus upon and have a look at. And let's have a look at only this part. Now, what is so interesting about this part? Let's say there is a human standing. Let's say there is a human standing on the surface of Earth, and actually that human will not be seen as a human in this view. He should be a very tiny dot. But then let's say there is a superhuman who will look like a human nevertheless. And what I want to draw here in this view is another orange line, which is probably like this. So the speciality of this orange line is that it is going through the center of Earth. So you see, somewhere here this orange point is the center of Earth, and this orange line is going through the center of Earth. That means this orange line is a diameter, and that means at this point on the Earth's surface that will be the vertical. So then let me draw one orange human standing here, and that is how the orange human will stand on the Earth's surface. So that superhuman is standing like this vertically on the Earth's surface. And if he is standing vertically, where is the horizontal for him? So maybe the horizontal for him I can draw in a pink color. So this is the horizontal for him, people. This is the horizontal for this particular human. So now you have, okay, let me redraw it. So this is the horizontal for this human. So this orange human has got this pink horizontal and has got this orange vertical. And what he does is he takes this pink horizontal here. So he draws a plane which is a horizontal plane for him like this. So these two pink planes are horizontal planes. Let me make a mention of that here on the diagram itself. So horizontal, and I'm doing it here, people. Horizontal planes, this one as well as this one. So these two planes are horizontal planes, and this person will see that the total magnetic field of Earth in a vertical plane is angling below the horizontal. Let me show you that angle also in a different color. Maybe I'll take wine red color. So you focus on this point, people. This guy will see that the magnetic field is along this wine red line like this, or maybe that's not visible, so I will take a different color. So this red line there, yeah, that is, I think, better, right? So this human feels that the magnetic field of Earth at this point is pointing below the horizontal, and specifically it makes an angle delta with the horizontal like this. So you are able to see that angle, I believe. So it's a bit difficult to appreciate that angle, but then if you have got a hold of this diagram, I think you will be able to follow when I draw it again in my hand, So keep in mind that this human in the northern hemisphere will feel that the field line is going below the horizontal, and it makes an angle delta with the horizontal. Now what will a person standing in the southern hemisphere say? So for that I took a view of inverted Earth. So you can see that this is inverted Earth, this is inverted Africa, here there is Middle East somewhere, this is inverted India, this is Australia somewhere, so this is Antarctica. Now I want you to focus upon this particular line, the one that I'm shading in pink now. That is this line, people. So let's only focus on the starting point of the starting segment of this line, and I'm going to do the same thing. I'm going to draw a line that is going through the center of Earth. So maybe I draw that line like this. So you see, this is a line that is going through the center of Earth. Roughly, the center of Earth is here somewhere. So that cross is the Earth center. And so if there was a human standing here, that human would be standing like this. And for this human, this orange plane will be a horizontal plane. And when he draws a plane which is parallel to the horizontal, slightly above himself, he will draw it like this. So these two horizontal planes are these two orange planes are horizontal for this human. And what this human will see is that the magnetic field at this point angles above the horizontal. So it is angling like that, this blue line, So the magnetic field is angling above the horizontal, and it makes a certain angle delta with the horizontal. So two different humans in two different hemispheres seeing two different things. So the one in the northern hemisphere will see the magnetic field line going down the horizontal, and the one in the southern hemisphere will see the magnetic field line going up. And any guesses about which is the hemisphere in which most of the scientific research took place in the 1600s and 1700s and the 1800s, people? So because most of the research work, in fact not most, I would say, I will go out on a limb and say all the research work happened in the northern hemisphere here, what we observed was that the magnetic field always dips below the horizontal. And that's why this delta has been called the angle of dip. So let me now define what is angle of dip. Angle of dip. In the magnetic meridian, it appears in the northern hemisphere that the magnetic field dips below the horizontal. And the angle that the net magnetic field makes with the horizontal is called the angle of dip. Needless to say that this angle of dip will be different at different places on the Earth's surface, and for the same magnetic field line also, the angle of dip will keep on changing. For example, if you just have a look at this pink colored line, the angle of dip initially will be something else, the angle of dip afterwards will be something else, the angle of dip at some other place will be something else, and it is closest to the equator roughly that the angle of dip will be 0. Why will it be 0? I will show you that in that 3D model, people. So let's have a look at what happens if you are standing near the equator somewhere. So first of all, let me erect the Earth. So now this is a view of the erected Earth. Here you see South America in front of you, and this is it. Now what I'm going to do is I'm going to look at another view. So here is the equator somewhere. You see there is the equator somewhere here, and I want to see what happens if a person is standing right at the equator and sees one of the field lines. So maybe I will not be able to draw that view or see that view here because I don't have that ability to, I think, rotate this in that view, but I will just try nevertheless. Can't, no, that view is hard to come by. Okay, So let me just show you what happens here. So maybe if you look at the viewpoint from a person who's standing here, and to draw the person here, what I will do is I'll take a different view. I'll just take a screenshot of this, and I'll take the screenshot away to my notebook, people. So just a moment. So the view that I wanted to show you. So maybe let us draw a vertical at some point on the Earth's surface, which is like this, So let's say that this is the vertical at some point. So where are those points where this line is the vertical? So this is the center of the Earth here. This is the center of the Earth, and maybe I'm talking about this point. So there is a human standing here like this, or maybe there is a human standing here like this. So whichever human you think about, the horizontal will be another orange line like this for the human standing on the left hand side, and for the human standing on the right hand side, the horizontal is going to be this line. And you see that when he looks at the magnetic field lines which are right overhead, and he tries to draw the magnetic field's net direction, you see for this line, let me show you, he will say that the magnetic field is like this, and he will say that the magnetic field here is like this arrow, and he will say that the magnetic field here is like this arrow. So you see that this is roughly the horizontal for him, and he will say that the magnetic field is totally horizontal. So the angle of dip is going to be 0, very close to the equator. I'm saying very close, it's not exactly the equator because the magnet is not really aligned geographical north-south. It is at a certain angle at a certain place, and that will affect the exact latitude at which he will see this, but that latitude will be close to the equator. And similarly for the other person on the other side. So this person will say that the magnetic field lines are like this, these arrows, So he will speak about these arrows, and he will say that yes, the magnetic field is perfectly horizontal and the angle of dip is 0. So both of these humans will, in fact, the opposite directions, people. This is pretty bad what I've done. So these arrowheads must all be in the other direction, because the north pole of the Earth's magnet is here somewhere, and that is going to emit out the field lines, and the field lines are going to go in that direction. So my bad. Kindly have a look at the arrows again. First on the left hand side, so like this, and then like this, and then like this, and then like this. So the reason behind decreasing the size of the arrowheads as I go up is that the magnetic field becomes weaker and weaker as I go away from the Earth's surface. So like this probably. And this person will say that the field lines are again like this, like this, like this, like this probably. So that's how the field lines are. So here also he sees the field lines, here also he sees the field lines, and both of these guys will say that the field lines are perfectly horizontal, so the angle of dip is 0. So keep in mind that this angle of dip also varies from place to place. On the same field line, if somebody was to go towards the southern hemisphere or towards the northern hemisphere, the angle of dip will not be 0. So along the same magnetic field line, the angle of dip keeps on changing. So keep that in mind. Now, if you have understood the angle of dip, let me go to something else. Yeah. So let's have a look at this figure, people. And before we have a look at this figure, I just want to define a new symbol which I will be needing help of. And so I'm going to maybe define the new symbol here. So when I draw something like this, when I draw one orange line like this, and I show this, that you can assume that I'm seeing from the top, and this guy is a human, and the back of his head is here. This is the back of his head, and these two are his eyes, so that he's facing here, facing here. So this is the convention. So maybe if I draw it like this with the two things here, I want to show you a human who is facing here, facing here, like this, the arrowhead direction. If I draw a human like this guy is facing there, so facing here. So please keep in mind this kind of a convention, because that is going to be useful here. And so let me first copy this. Let me take two of these figures. So it's important to have two of these. Yeah, fine. So let's first of all go for this figure and say that there is a person who is facing this way, which means he is standing in the vertical plane that we are calling the magnetic meridian. So this person is facing this way, and so he will see that a field line goes right overhead, and then the field line basically goes overhead from this side to that side, because the field line should start emerging out of the earth here, then the field line should turn around, and then that should go overhead this guy, and it should go into the North Pole there. So he feels that a field line is going right overhead, and not just that, he will also see that the field line makes a certain angle with the horizontal. Of course, he will not be able to see that angle from this view, but then he will be able to reduce that angle. Let us ask him to reduce that, and he will say that a field line is right overhead and the field line makes a certain angle with the horizontal. And let me draw that view for you here. So what he says is that he is able to see something like this. So this is a vertical plane, and that human is standing here somewhere. So this is that human standing here, and he sees a field line going right overhead but also turning in a certain way. So maybe he sees this field line, and he sees the field line dipping below the horizontal at a certain angle. So he says that the field at this particular point is angling like this. This is the magnetic field at this particular point, and this magnetic field has got two components. One is its horizontal component, BH, and the other is its vertical component, BV. So this is BV, and he will find that delta, this guy, is the angle of dip. And the equations that he can write, so let me call this guy B net or simply B. And the equations that he can write are, he will say tan delta is equal to BV by BH, or let me just show it to you on the right hand side. So knowing any two of these four variables, he can find out the other two. So say for example, he knows B. So if B and delta are known, then BV is equal to B sine delta, and BH is B cos delta. So if he knows B and delta, he can find out BV and BH, no big deal. Usually, so this is one, sorry. Usually we know B horizontal and we know delta. So let us go from that angle. If BH and delta are known, then what can we do? Then we can say that tan of delta is going to be BV by BH. That will mean BV is equal to BH tan delta, and this is one relation. Second, and then he will say B net is equal to root of BV square plus BH square. He can find the magnitude this way, or maybe he can use again he can use maybe cos or sine of delta to find out the value of B. So we can figure out any of these if we know the other two. So out of these four, if you know just two, you can find out everything else. That is one thing. But all this is happening in this vertical plane, which is the magnetic meridian, because this person is standing facing this side and his back is that side, and he's standing with his shoulders. So the line joining the shoulders is this line, the orange line, and that is perpendicular to the magnetic meridian. So this vertical plane that this person is talking about is the magnetic meridian. Let me make a note of that here somewhere, magnetic meridian. And then let me ask you a follow-up question. Suppose you have a human who stands at the same place on the Earth's surface. So this person was standing in the Indian Ocean somewhere, maybe with floaters or something, otherwise he'll sink. So maybe the second person also stands in the Indian Ocean somewhere, but what he does is, or maybe the same person. So what the same person does is, now he gets bored of standing like this and he turns. And now he stands like this. These are, so this is the line joining his shoulders and his eyes are here, maybe, So he is now facing this way. And when he faces this way, he sees that the magnetic field is going overhead. Yes, true, the magnetic field is going overhead, and that magnetic field is angling also. But then he will be able to see, so in the direction of his view. Now I want to ask you whether in the direction of his view, that is along this dashed orange line, will he see any magnetic field component? Have you understood the question? Will he be able to see any magnetic field component along this dashed line? And before you answer that question, let me give you a hint for that. And the hint is this. So let's go for a different view, and maybe this person turns around, but not that much. So maybe the person is standing here like this. The line joining his shoulders is this particular orange line, and his eyes are also here. So like this, and he's facing this way. So you know that standing in a room, you can face any horizontal direction. So this human is now facing this horizontal direction, but the horizontal component of magnetic field, BH, is in this direction. So let me draw that BH also, people. BH is this orange line, BH. So how can I make it more prominent? Maybe I can write in black. Yeah, that is a bit more prominent. So this is BH. So this is the horizontal direction in which the Earth's horizontal magnetic field lies. But now he has turned around, and his line of sight makes a certain angle with that magnetic meridian. So will he be able to see the complete BH, or will he be able to see a different amount of magnetic field along this line? And if it is a different amount, will you be able to give me the answer of how much is that magnetic field in terms of the angle here? Maybe I call this angle as theta or something. So if I call the angle between these two directions as theta, will you be able to tell me how much is the magnetic field observed by him? Let me call it BH prime, to show that now this person observes a different horizontal magnetic field component in that direction. How much will be that in terms of this guy, BH? As all of you have answered, in this view, the value of BH prime will be equal to BH cos theta. So let me just make a note of that fact here. Maybe here is a good place to write it. BH prime will be equal to BH cos theta. So this person who is now facing this way will only be able to experience a part of this magnetic field, the horizontal magnetic field, but he will still be experiencing the complete vertical field, because you can do this experiment in your room, standing in your room, standing at the same place. If you just turn around 360 degrees, you will be facing a different horizontal direction every time, but then the vertical for you will remain the same. So if the vertical for this person remains the same, the vertical field for this person remains the same, and the horizontal fields component keeps on differing. So if I say that he is experiencing a vertical field BV prime, I can say that is equal to BV itself. So keep in mind this. And then this person who is facing in a direction that is perpendicular to the magnetic meridian, for this person BV prime will still be equal to BV, but BH prime will become BH cos 90 degrees, which is going to give him a 0. So this person will say that there is no horizontal field at all, because all the horizontal field is in a perpendicular direction, and you know that if you take a component of that field along this line, that will be a 0. So please keep that in mind. So based on what is the direction in which we are facing, we will observe a different BH, but the BV remains the same. And that means standing at the same place, if I am facing like this, and if I try to find out the angle of dip, I get a different angle. If I face like this and I try to find out the angle of dip, I'll get a different angle. And facing like this, if I try to find out the angle of dip, I'll get a different angle. The reason is very simple. Let me just show you in a diagram. So maybe I will take the magnetic meridian, which is this particular plane. So keep in mind that this plane is the magnetic meridian. And let me take a different plane, people. Let me take a darker color to show you that different plane. Maybe like this. Yeah. And yeah, okay, maybe like this. and then maybe like this. Yeah, so this is a different vertical plane. So you have got a pink vertical plane, that's the magnetic meridian, and the person may face in this direction, rightwards. Then there is a dark violet kind of a plane, vertical plane, and if a person has to face in that direction, the person's gaze or view will be angling into the screen like this, right? And the angle between these two is theta. So what is going to happen is that in this magnetic meridian, the magnetic field's horizontal component is BH, that is this pink arrow, BH, and the vertical component is BV, that is another pink vertical arrow, BV, and the net field in the magnetic meridian is going to be, let me draw it using blue color, and that's going to be, oh yeah, sorry, that's going to be this one. This is the net field. So this is the net field which is there at that place, and this is how it will look like in the magnetic meridian. So maybe I'll call it B net. But what happens in the other plane? So if a person is facing in the direction of that dark violet plane, what happens is he will not be able to see this complete BH, and he will have to draw a perpendicular from BH onto that plane. So let me take that also as a dark violet color, like this, like this, like this, and this much. So he will be able to see a smaller field in that direction horizontally. And then if I just focus on what is happening in that plane, let me just copy this figure, paste it, and let me just focus on what is happening in that plane. So let me erase these unnecessary things here. Yeah, so these are gone. And now what that person will see is this. He will draw this line like this, and then he will draw probably this line like this here, and he will see, let me remove certain portions of these lines. Yeah, and the person, when he is facing in that direction, in the dark purple direction, will be able to see a net field which will be shown by this wine red color like this, and the magnitude of this net field will be different from the magnitude of this net field. In fact, now I can remove this angle theta. I will throw away this angle theta from these diagrams, and I will show you this angle theta in a different place perhaps. So I think a proper place to show this angle theta will be somewhere here like this. So this is the angle theta that I'm talking about, and here it is theta, the angle between these two planes. And now in the left hand side diagram, let me show you the angle of dip here. That's going to be this angle delta. That's the angle by which the magnetic field is dipping below the horizontal. So this is a horizontal in the magnetic meridian, and the dark violet line is a horizontal, but it is making an angle with the magnetic meridian, and the angle of dip there will be delta prime. So let me call that as delta prime, and BH prime, let us say. Right, so now I can write expressions for delta and delta prime, and from the expressions you will see that tan delta is going to be BV divided by BH, isn't it? Tan delta is going to be BV divided by BH, and in this figure you will see that tan delta prime is going to be BV divided by BH dash, and from here you can deduce easily that since BH prime is less than BH, therefore tan delta prime is greater than tan delta, that means delta prime is greater than delta. So if you are not standing exactly in the magnetic meridian, you will be able to see an angle of dip that will be greater than the actual angle of dip. So that's one thing. So that means if I keep on deviating from that, I will be able to see larger and larger angles of dip. And until where will the process continue? So it's very clear that the process will continue till a time you are standing exactly perpendicular to the magnetic meridian. Now how do I draw that view? I'll just make an attempt, people. Maybe like this. So let me draw a light plane, and let's say this light plane is the magnetic meridian, this one. Yeah, and let me draw another plane. So this plane is the magnetic meridian. Let me draw another plane that lies there in the other direction. So how can I draw it? Maybe like this, and then I have to rotate this. Like this perhaps. Will it work? Will it work now? Yeah, that looks very much like it. So let me keep it here and try to rearrange. Yeah, that seems very much like it. And let me take this guy also up and shift the diagram below. Yes, people. So the diagram looks like this, right? Where this pink one is the magnetic meridian, and let me just change the sizes. Like this, yeah. And this much works fine. Yeah. So this looks really nice, neat, and let me group this. So this plane, the pink one, is the magnetic meridian, and the blue one is a plane that is perpendicular to the magnetic meridian. Magnetic meridian. And this blue one is a plane perpendicular to the magnetic meridian. And let me draw the field components. So you've got BH here, so you've got BH here, this is BH, and then you've got BV here, down BV, and then the component of BH in a perpendicular direction will be 0, so you have got no field there horizontally in the blue plane, nothing whatsoever. So if you keep a compass needle, so maybe I take a compass and I keep that compass in the magnetic meridian like this. So this is a compass needle in the magnetic meridian. How is it going to face? Compass needle in the magnetic meridian. So please keep in mind that this is not the usual compass, because the usual compasses are used in a horizontal plane. This guy is in a vertical plane. So this is a compass needle in the magnetic meridian, and the compass needle will show you probably this direction, which is the direction of the net field in the magnetic meridian. But if you keep the same compass needle in a different plane, if you keep it maybe in this plane, the other plane that we had, right, like this. Yeah, so if you keep the compass in the blue plane there, so let me make the compass also blue. So if you keep a blue compass like that, then that compass needle is going to be only under the effect of BV, and so that needle will only be vertically downwards. So keep in mind that the needle will be vertically downwards, and so this is a wonderful check to find out what is the plane in which you are standing. In fact, if you want to find out the true angle of dip, this is the first step. The first step is that you take a compass needle that can be kept in a vertical plane and you rotate that compass needle's vertical plane slowly till you reach a plane where the compass needle is completely vertical. So the plane in which the compass needle is completely vertical is a plane which is exactly perpendicular to the magnetic meridian. So then you turn by 90 degrees and then you are standing in the magnetic meridian. And then in the magnetic meridian, you have the true horizontal field and you anyways have the true vertical field. So the angle that the needle makes with the horizontal, this angle delta is the angle of dip, and that is the true angle of dip here, people. So that's how we can figure out what is the true angle of dip, and we can also figure out which plane is the magnetic meridian and so on. So that is about the magnetic field of Earth and its elements, people. I hope you have really understood what is the magnetic field of Earth like. Please keep in mind that I've got two ratios here. Tan delta is BV by BH and tan delta prime is BV by BH prime. Now BH prime is small because BH prime is a component of BH. BH prime is, let me make a note here, people. BH prime is going to be BH cos theta. So because BH prime is small, that's why this ratio is large, and that is why tan delta prime is large. And we know that in the 0 to 90 degrees domain, if the angle increases, then the tan also increases, and vice versa. If you know that the tan is more, so the angle is more. So delta prime is more than delta. And if you are standing in a plane that is perpendicular to the magnetic meridian, you will get that delta prime is 90 degrees. That means tan delta prime is infinity, and that is expected because the horizontal field becomes 0.